Here we will see the properties of LC driving point immitance functions. So we have seen impedance and admittance, but what is meant by this immitance? So immitance is a common term given to the impedance as well as admittance functions, right? Rather than conveying it like admittance or impedance, a common term is used as immitance. Fine, right. So we will see LC driving point immitance function properties, using which we can test whether the given function is LC function or not. Okay, right. So what is the first property? First property is that it is always the ratio of odd to even or even to odd polynomials. Okay, we all know even terms and odd terms. We have seen also solved many problems with Hurwitz as well as positive real function concepts. So accordingly, LC function is always a ratio of odd to even or even to odd. Okay, so second property is that the poles and zeros are simple and they lie on the j omega axis. This is important. We are not going to have any poles on either left half of the S-plane or right half of the S-plane. The poles and zeros are going to be lying on the j omega axis and they are also simple. Okay, right, because we should not have any repeated poles on the j omega axis for a positive real function. So it is a simple check. Right, the third property is that the poles and zeros interlace on the j omega axis. It means the j omega axis poles and zeros are going to be coming continuously, like means alternatively. Interlace means alternatively. If there is a zero, then next you have to get a pole only. There will not be any continuous zeros or continuous poles. That is the meaning of interlace. When you see the problem or example, you will understand this. Right, the fourth one is that there must be either a zero or a pole at the origin and infinity. Okay, either a zero will have or a pole will have at the origin and also at infinity. And the fifth one is saying that the difference between any two successive powers of numerator and denominator polynomials is at most 2. So at most means it is maximum 2. We cannot have more than that. We can have 1, but we cannot have more than 2. That means we can have 1 and 2 only, up to 2. And there cannot be any missing terms. When you see the numerator and denominator, you will not have any missing terms. That means if s power 4 is there in the numerator, s cube will be there in the denominator. That's it. So like that you need to check continuously for numerator and denominator. All the possible degrees will be there between maximum and minimum degrees. Okay, then the sixth one is saying that the highest powers of numerator and denominator polynomials must differ by unity. And there is one more point in the same. It is also saying that the lowest powers also differ by unity. Okay, both highest powers as well as lowest powers of numerator as well as denominator are going to be differed by unity only. That means by 1 only. Otherwise it is not a LC function. Okay, so let us see an example. So we will see here an example where two different functions, impedance functions, are given, and we need to check whether they are LC functions or LC networks or not. So okay, right, let us see the first one. Z of s is equal to 5s into s square plus 4 divided by s square plus 1 into s square plus 3. So if you see, there is a 0 at s is equal to 0. One of the properties there. And we have all other poles on the j omega axis only. Not only poles, also zeros as well. Okay, but we will check the interlacing property. Whether if we have any poles or zeros continuously, then it is not an LC function. Right. Okay, let us see. First you mark all the poles and zeros on the j omega axis. From that you can easily tell. So if you see here, there is a pole at j root 3, and just after or just below that we have one more pole at j1. So what you can observe here, there are two poles which are continuously coming without any zero in between them. That means they are not interlacing. So with that property violation, we can directly say that the given function is not LC function. Fine. Okay. Then we will see the next one, z of s. So here this is the function that is given. So right, if you see, we have 0 at infinity. Fine. And we have poles and zeros on the j omega axis only, which are given like this. So first you identify them and mark them on the j omega axis of the s plane. Then you check the alternative property of zeros and poles. So we have a 0 at this one j3, and then we have a pole at j root 2. Then below that we have 0. Then again we have pole, 0, pole, 0. Right? That means they are alternatively coming. There is no continuous 0 or continuous pole. Right? Then interlacing property is also satisfied. Right? Okay, so even if you check all other properties, they will be satisfied. Right? Fine. So with this you can say the given function is LC impedance function or LC network. So here in this example, A is not an LC function, whereas B is a LC function. So this is how you are going to check the properties and identify whether the given function is LC function or not. Fine. That's it.